All right, so I did a little bit of work on this one off camera. I just wanted to plug these values in so I didn't waste time doing that in my calculator on the video. And so everything's ready to go. The only thing we need to do now is we need to determine the polarity of these voltage sources, okay? So let's summon in our dot convention helpful hint here. I'm going to copy that over again. Just paste it right here. All right, so let's take a look at the dot convention. What we have is positive current into the dotted terminal of 1. So again, I1, which I'm sort of defining flowing this way, is going to flow into the dot of L1. That's going to force a current, not I2, an independent current, out of L2 at the dotted terminal, out of the dotted terminal. In other words, it's not flowing out of this terminal. It's not flowing in this direction. It's flowing in the bottom and out the top. It's flowing out of the dotted terminal. The voltage source that is induced needs to force that current to flow in that direction, okay? So because I need it to flow this direction, out of the dotted terminal, right, into the undotted terminal and out of the dotted terminal, I need the polarity to be such. Okay, so that's the polarity of the first one. And this right here is the mutual inductance. This is the current that induced it. So I times the impedance of that mutual inductance, okay? And so we can go ahead and just draw that over here. Same goes for the other one, but we're going to look at I2. In this case, I2 is flowing in a direction such that it flows into the undotted terminal, out of the dotted terminal. Flowing out of the dotted terminal here means that it needs to force a current into the dotted terminal here, completely independent of I1, has nothing to do with I1. This is an independent current. It's dependent on I2, okay? I keep calling it independent. I mean, it's independent of I1. It's dependent upon I2 in this case. And so in order to force a current in this direction in the circuit, I need a voltage source that's going to force a current in that direction. And so to force current in this direction, I need the polarity such that the plus is here and the minus is here. Okay? And so we're going to go ahead and put that here, plus minus, just like that. And now we're ready to solve this circuit. And you'll see that we got basically the exact same polarity here that we got in the previous example because the currents were defined the same and the dots were in the same position. If we define the currents differently, we will get a different polarity here, but it should all work out the same because again, if I define one of my currents flipped, the negative of that is just true. It's the same way in EE220 that we said, you know, you can define a current this way, but then if that current comes out negative, then you know that it was actually flowing positive in the other direction. The same goes here. You can define these currents however you want, and then when you set this up, you know, if you were to flip the polarity of this source, you know, to the other way around, let's say instead you put the plus here and the minus here, right? Now you'd solve this, you'd get some value for I2, and maybe it would be 180 degrees phase shifted from the correct value. That's totally fine because, you know, at the end of the day, a negative current means very little in terms of AC. It was more relevant in DC, but the bottom line is the point is you can define the currents however you want, and it's going to work out as long as you keep the dot convention straight. Okay, so here we are. We can solve this circuit now. I'm going to actually just copy and paste it over to the next page here. Let's do that. Sorry. Let's move on over here. And let's go ahead and write some expressions. So for the first loop, actually let's draw our pluses and minuses. I go plus minus, plus minus, plus minus, plus minus, plus minus, plus minus, just like that. And what I want to do here is write an expression for the first loop. So I'll go 10. I'll drop the angle 0, of course, because we know that that's just going to be 10 in rectangular. Then I'll go minus I1 times, and I've got a series impedance here, right? I've got 3 different impedances. I've got 5, then I've got minus J 15.9, then I've got plus J 6.28. All right, you could write those all as different terms, but not really any reason to do that. Might as well just group them from the start. And then I get to this voltage source, and I know I'm going from a minus to a plus, so I have to go up in voltage. So I'm going to add I2, J 3.14 equals 0. That's my KVL loop for the first loop there, my KVL expression for the first loop. Okay, so let's write the expression for the second loop. I'll start here and go this way. I'm going from minus to plus across the voltage source, so I'm going up. So I'm going to write a positive I1 times J 3.14. Then I go minus, and again, I've got 3 impedances here. J 18.85 minus J 15.9, and then a plus 20. And that whole thing is equal to 0. Okay, so we're set up. We've got our equations, and I am going to probably end the video here. I don't actually know if this one's gotten super long yet, but I'm going to end it here, and then we'll just wrap up by doing the 2 equations, 2 unknowns in the next video, and then we'll call it. This example will be done. As soon as we find I2, we're after IL here. We're really after IL of t, which comes from IL, the phasor, which comes from I2, because I2 and IL are basically the same, right? So we're going to go ahead and solve those 2 equations, 2 unknowns. Once we get a value for I2, we're good to go. So I'll go ahead and end this video, and we'll see you guys in the next one where we wrap up this problem.